Alright fools, welcome to the third video. In this video we're going to go ahead and start and design the objective function. The objective function is the most important part of any optimization problem, and it generally represents the residuals between our model and the targets. So the targets for this are 4.3 and 9.1. Okay, so now what we want to do is we want to figure out what is our actual gear ratios, because we're starting at this initial guess here, and this might not work, you know. So we need to see what the error is of this compared to our target ratios, and so we will design the objective function around that. Again, in the interest of readability, I'm making these comments here. Okay. Okay, so let's just call it the objective function. Call it whatever you want. We're going to pass the model to it. Okay. So now I'm going to define these variables, or these, you know, what have you, R1 and R2. For residuals 1 and residuals 2 will be the residuals between the forward and the residuals of the reverse, or the residual, since there's only one value. So since we're designing with this configuration in mind, so that means that we're having the idler gear be on the output, and on the reverse side, and the idler is connected to the output shaft. You can design a gearbox where this setup, this 6, 7, 8, is actually over here on the input side. And actually that will give you a smaller face width when we start talking about stress, because on the input shaft there's not a whole lot of stress, but on the output shaft there is. And we know that because on the output shaft we have 4 times the torque in the forward gear ratio configuration and 9 times the torque in the reverse. So that means that the output shaft has to take a lot more loading. So if you want, you'll design this so that this is on the input side. And if you just learn about gear ratios, that will be easy for you to do. But again, we're going to be solving this problem here. Those of you reading or watching may not care to design it this way, because it's not that smart to design it this way. Again, because the idler gear has to take a lot of stress. So you don't really want to have it be on the output side, but I didn't realize that the first time I went through this process, and so that's not what I'm going to be documenting. I'm going to be documenting the way I did it the first time. So let's go ahead and do that. So what we want to do is calculate the gear ratio. So we're going to do N2 over N1 and 4 over N3, and we're going to add this too. And if you look at these equations, if we move the 4.1 over, so this minus 4.1 should be equal to 0. Again, in real life it's not going to be equal to 0 though, because we're trying to get this as close to 4.1 as we can, but it's generally going to be hard to do. So we just want it to be close to 0. So after we subtract the 4.1 over, we want this side to be as close to 0 as possible. That's going to represent our error. So by doing that, we're going to represent that error. So let's go ahead and get into it. We're going to do model.d1, so that's the second gear, divided by model.d0, first gear, multiplied by model.d3, which is the fourth gear, model.d2. Okay, and after that we're going to subtract off the forward ratio, right? That's this right here, same equation. And we're going to get the absolute value, because we don't care, we don't want this to be negative, because we're going to be minimizing this function. So if we leave off the absolute value, basically what we're telling it is to get the farthest away from the forward ratio as we can, which we don't want. We do not want that. We want the closest we can get, so we did absolute value. Actually, you know what, in the interest of making this more readable, we'll just go ahead and do this instead, so we don't have to, you know, it's just going to be easier instead of going on the 0 system, which is kind of counterintuitive. It'll be easier to just do these 1, 2, 3 kind of thing. So that way we can just over here 4, 3. Now these actually correspond to what we're trying to do. So this is the error between our model and the forward ratio. Now this is the absolute value of the residual. You can do the least square of the residual if you want. It may be easier to solve. I haven't experimented with that, so we're not going to do that. We're just going to do this here. So now let's go ahead and do the reverse ratio. So we're going to do model.d5 times model.d, let's see here, model.d6, model.d, let's see, is this right? No. Model.d7, d6, model.d8, and model.d7. And now at this point you may be wondering, why do we include this one right here, right? Because as I demonstrated earlier, this 7 cancels out. Well, we could leave that out, but then we wouldn't be designing the idler gear, and we need to design the entire thing. So even though it's not going to come into play very much, we still need to design that. So we still need D7 to be a part of the whole situation here. Okay, so now if we want, we can just do this, return R1 plus R2. Okay, but traditionally we want our objective function to handle mostly all of the design variables that we're doing. So, and you don't have to do this, okay, but this is just what I did for this problem, and it may be dumb, and you may have a good reason for why it's dumb, but this is fine for me. So since we're designing here for D, now we want to design for N, right? Because these same expressions, they should hold for N as well as D. So we just create the same thing for N. To make this a little bit faster, I'm going to open up my text editor and find D and replace it with N. Boom. Okay. There we go. So now we have D's and then N's, and so we're going to return the sum of all of those. Boom. So there's our objective function. This is going to represent the total error, and again, the error on the diameters will actually be exactly equal to the error on the ends. The only reason that I include the n is just to have as many of the variables as I can in the objective function. There's really not a way to include the diametral pitch, the face width, or the center distance in the objective function. Instead, we will consider those as parts of our constraint. Okay, so now that we have the objective function, we're going to try to minimize this, but now we need to input all of our constraints. So I'll go ahead and declare constraint functions. We do def con fun1 model. So this is the first constraint function. Call it what you want. I just like to do this to keep it simple. So what are the constraints that we need to do now? So the first constraint that we'll tackle are the diametral pitch constraints. And these are the constraint family of keeping the number of teeth per unit length the same for gears that are meshed. So I spoke about this in the last video, but 1, 2, and 5 will have the same diametral pitch, 4 and 3 will have the same diametral pitch, and 6, 7, 8 will also have the same diametral pitch, but they'll all be unique. So, and if you don't recall, we initialized to those up here, 4, 5, and 18. So let's go ahead and do this. So for the syntax for defining PYOMO constraint functions is as such. We're going to just return return the diametral pitch for the first gear. Okay, sorry. So this is diametral pitch, right? We're going to set that equal to model.p1, first diametral pitch. Okay. Now we're going to have to go ahead and make one of these functions for every gear. So 2, 3, 4, 5, 6, 7, 8. Okay, and then so for conf_2, we're going to just change these to 2. But this is for the second gear, so we look over here. Second gear has the same diametral pitch as gear 1. So this is just going to stay at P1 here. Conf_3, model.3. Now 3 and 4 are going to have the same diametral pitch, and that's going to be pitch number 2. Conf_4, gear 4 is going to have the same as gear 3, so that's pitch number 2. And now we're doing gear 5. Gear 5 is going to have the same diametral pitch as 1 and 2. So we set that to 1 here. You can see that. And then 6th gear. And this is going to be the third and final pitch. Gear 6, 7, and 8 all have the same pitch. So set that to this. Boom. I'll rename these ones though. Okay, so that is the first family of constraints. We've handled the diametral pitch constraint functions are right there. The next family of constraints that we are concerned about are the center distance constraints. These are going to be the constraints that ensure that the center distance between 1 and 2 is the same as the center distance between 6 and 8, and 3 and 4, 5 and 2, and such and such and such. So let's go ahead and do that. Def conf_9 model. Okay, so the first one is going to be like this. Let's go ahead and open parentheses, return model.d2, or just d1, plus model.d2 divided by 2 is equal to model.c. Okay, and that's the distance between the two shafts. Okay, we're not worried about this idler shaft quite yet. Actually, it doesn't matter where the idler shaft goes, but we're just worried about the center distance here. So that was the center distance constraint for 1 and 2. Okay, so now we'll do, in a similar fashion, model.d3 plus model.d4 divided by 2 equal to model.c. Def conf_11 model return model.d So we've handled 1 and 2, 3 and 4, so let's go ahead and do 5 and 2 now. Now we'll do this last one. Since we've handled these ones, we'll do 6, 7, 8 now. 6, 7, 8 is not going to have the same form as the other ones. So we're going to do model.d6 plus model.d8 divided by 2 plus model.d7 is equal to model.c. Okay, and that is because D7 does not lie on the counter shaft or the output shaft. In fact, the entire diameter is included in the center distance here. So we have half of D6 plus half of D7, half of D8 plus D7. Okay? So those are the center distance constraints. The next thing that we're going to do is apply this constraint here. This one. Okay, so we need to make sure that B for any given pitch is, any given face width is in between the corresponding pitch constraint 9 over P and 14 over P. So declare, we'll just call this pitch face width constraints def con fun 13 model. Okay, and this is going to be the most irritating part of all the constraints. So basically there's 3 face widths, 3 unique ones, just like the pitch, 3 face widths, 3 diametral pitches. The irritating part about PYOMO, and I understand why they have to do this, but it doesn't mean it's not irritating, is that we can't do something like this, because this is what we really want to do right here. This is what we really want to do, right? But in PYOMO, it won't let